Okay, so today we will take a look at the chem mechanisms. Chem mechanisms. So what is it chem mechanism and what is it good for? So chem mechanism contains a general link. And what is it good for? It's good for the transfer of motion. Transfer of motion. For example, when we have a translation, so this is translation, and here is the general link, and we have always one motion that is primary and a secondary motion. So in this case we have translation and the secondary motion is rotation. So if this motion is given, for example, by velocity and acceleration, then we have transfer of translation to rotation. And we can make chem mechanism for all the combinations. For example, if we will have a translation, then this could be also translation. So we have translation to translation. And we of course can have a rotation, for example, like this one. So we have rotation, which is primary, and that is transformed to translation, and we can have rotation and rotation as well. So here is the general link, here is the general link, and we have rotation and rotation. So we have rotation to a different type of rotation. Now this is typical, for example, for the valve control in the internal combustion engine. Now how do we solve mechanisms that contain the general link? How do we solve the chem mechanisms? There are several methods. Well, the most popular one among the students is, so the method is the method of supplementary mechanism. So how does it work? We replace the essence of the method is replace of general joint or general link, general joint, by new body. Okay, and how is this new body connected with the previous bodies depends on how the general joint, general link is actually made. So there are basically four categories. The first one will be a curve on curve. So in here we have a curve on curve. This is body number 2, body number 3. These joints are not important. Whether this is rotation or translation, it doesn't really matter. What is important is that we have a curve on a curve. Both these curves have certain center of curvatory. So this is S2, this is S3, and this new body that we will add in here has, in this case, rotation links. So this will be our new body number 4, and the rest is the same. So we can replace it with this. So this will be our new body number 2, our new body number 3. And this chem mechanism then changes into this 4-bar mechanism. Now, the important thing is that this 4-bar mechanism, the supplementary mechanism is valid only in this particular moment, only in time t that we are actually examining the mechanism. Why? Well, because whenever there is a motion of the mechanism, then for example, the dimension, the distance between S2 and S3 can change. Okay, so we have to adjust the supplementary mechanism accordingly. Now, the second case is when we have a curve and a line. Again, let's, for example, put the rotation links here, number 2, number 3. So in this case, the curvatory radius in here is infinity, while for this curve we have S2 here. In this case, for the curve we have a rotation, and for the line we have translation. So this little body number 4 is our new body in the mechanism. Again, this is new body number 2, and body number 3 is unchanged. Okay, so this is a curve, and this is curve, line. Okay, there are 2 more cases. The first one is a curve and a point. So this is body number 2, and this is a point. Usually, if we would magnify this part, there is a additional body that ensures that the friction in this part is negligible. Anyway, now when we have a curve and a point, then for the point there is a rotation link, and this, for example, has S2 in here. So we have a rotation again. So this is body number 2. This is our new body number 4. And the final case is a line and a point. So body number 2, body number 3, and we have a point and a line. So in this case, whenever there is a point, there is a rotational link, and whenever there is a line, there is a translation link. So this will be our new body number 4, which we can connect in here. So this will be new body number 2, and the 3 remains the same. So in here we have a curve and point, and we have a line and point here. And well, basically that's it, because once we have the supplementary mechanism, all we have to do is use all the previous knowledge to solve the mechanism. Okay, just to be sure, let's make an example. And that example could be, for example, the valve in the internal combustion engine case. Okay, so let's have this body number 2, which is connected, for example, here with the frame, and has got the center of this circle is here. So this is our camshaft, basically, and we have a valve in here. That will be our body number 3. Okay, so, and we know how is this rotating, so we will have omega to 1 and alpha to 1. So we know the angular velocity and angular acceleration of body number 2. And what we want to find out is, let's call this point, for example, M. We want to find velocity and acceleration of this point. So this is our example. So the first thing we have to do is to find out the supplementary mechanism. So we have a curve and a line. Therefore, we have our new body is here. So this is our body number 4. And because 2 performs rotation and the center of rotation is here, so this is our new body number 2. Okay? Alright, so now all we have to do is to solve this new mechanism, and we will use the Coriolis method. We will use the combined motion. So body number 2 is performing rotation. Body number 3 is performing translation. And body number 4 is performing general planar motion. And we can write down the symbolic equation for the body number 4 because it's not connected directly to the frame, so we will use the combined motion approach. So the symbolic equations will be 4, 1 is, we can go to the frame through 3 or through 2. So that would be 4, 3 plus 3, 1 this way, or through number 2, 4, 2 plus 2, 1. Now all we have to do is find out a point where we will actually solve these symbolic equations, and the one point that has certain relative motion equal to 0 is this point S2. So we will, let's call this point, for example, I don't know, A. So in point A, 4, 2 is equal to 0 because there is no relative motion between 4 and between 2. Okay? Therefore, if we will put these together, 4, 2 is 0, so 4, 1 is equal to 2, 1. Only in here, of course, we will get that 2, 1 is 4, 3 plus 3, 1. And we have a symbolic equation that we will solve. Okay. So let's do it. Again, what is important is that we do this in point A. So we can write down the vector equation for velocity, VA to 1 equals VA 4, 3 plus VA 3, 1. So now we have the vector equation for the velocities in point A, and we just solve the equation. So let's take one component at a time. VA21, that's how body number 2 is moving in point A. We know omega to 1, so we know everything in here. the magnitude of velocity is omega 21 times the distance between A and the center of rotation. So let's call this point O21 and O21A, the distance. Okay, omega 21 goes clockwise, so here we will have VA21, and we know both direction and the magnitude. Now for 3, how is body number 4 moving with respect to body number 3? So we can imagine that 3 is not moving at all, and 4 is performing translation, right? Because that's given by this joint here between 4 and 3. So we know direction, and this direction is parallel. It depends only on this joint. So we know direction. So this is direction of VA43. And finally, we have here VA31. That's how body number 3 is moving with respect to the frame in point A. So body number 3 is here, and its motion with respect to the frame is given by this link, this joint. So it's moving up and down, right? So this is direction of VA31, and we know direction. Therefore, we can solve this equation because we have two unknowns in the vector equation in 2 dimensions. So to solve it, we have VA21, and that equals VA43 plus VA31. So this is the left side of equation, and that equals these two vectors. So this will give us VA31, and because 31 is translation, then VA31 is the same as what we are trying to solve. So this is directly velocity of point M, and we have the first part of our example done. So we can now move to accelerations. So AA21 equals AA43 plus AA31 plus AA Coriolis. And again, we will solve this equation by taking one component at a time. So 2,1 is rotation. Therefore, it has got two components, normal and tangent. Normal component is known, right? It goes from here to the center of rotation. It's here. The magnitude of the normal component is VA21 squared divided by the distance from the point to the center of rotation, that is AO21. The tangent component is depends on alpha and the distance. Therefore, we know it again. The magnitude being alpha 21 times the distance, which is O21A. And okay, I didn't put at the beginning where it goes, so let's assume that it's going also in the clockwise direction. So therefore, for example, this will be AA21 tangent. Now force 3 is translation, therefore it only has one component, and we know direction, which is the same as direction of AA43. AA43 is the same direction as VA43. 3,1 is translation, going up and down. So again, we know the direction and we don't know the magnitude, but it only has one component. And the Coriolis, well, this one is easy, right? Because it's 2 omega carrying 3,1 times V relative, VA 4, 3. Now, because 3,1 is translation, then omega is equal to 0 and the whole component is equal to 0. So there is no Coriolis here. So what we have to do now is just to solve this equation, which should be pretty simple, right? So we will start with the left side of equation, VA21 normal plus VA21 tangent. So this is the left side of equation. No, this is not V but A, sorry, acceleration. So again, AA21 normal, this component, plus AA21 tangent, AA21 tangent, that's this component, this one, and that equals right side of equation. And here we have only two directions, AA43 and AA31. So 43 direction is the same as direction for velocity, and 3,1 again is the same as direction for velocity because it's translation. So how about the arrows? So this is the left side of equation, jump, jump, and that has to be the same as the right side of equation. So 1, 2. Okay. So this way we will get AA3,1. And again, because 3,1 is translation, this is the same as AM. So this is the same as AM. And we solved our example. Therefore, it's essential for you guys to understand how to use the combined motion approach, because whenever you have the chem mechanism, the only thing that is different is that you have to build a supplementary mechanism and then solve it. Okay, so that's all for the chem mechanisms.